All right, so this is the fourth and final lecture on energy and the first law of thermodynamics, the introduction to it. We wrap up this chapter. A few things that we didn't really touch on. We didn't really do a rate problem. So I want to solve a rate problem, and then I want to touch about the generic cycle analysis for power cycle, refrigeration, heat pump cycle, and that'll pretty well finish it. Last time we talked about solving cycle problems on a PV diagram, going 1 to 2, 2 to 3, 3 to back to 1, as well as for a process, constant pressure process or expansion process or something. Okay. So the rate form. How do we get the rate form? Well, the rate form is something like the rate of change of energy in our system with respect to time will be the rate at which it flows in by heat minus it flows out by power. That energy is made up of internal, kinetic, and potential energy. Often we get tired of writing all three of those. We just say CAP-E, the total energy of our system. And so how do we get this equation? Well, we would write maybe the differential or infinitesimally small change form of the energy balance equation, which would be a small change in internal energy plus a small change in the kinetic energy plus a small change in the potential energy is equal to the small amount of heat transferred in minus the small amount of work transfer out. So those are all small or infinitesimal amounts. We divide by our small time, thinking about rate. We think about, 1 second, 1 millisecond, something like that. And now that turns into power, a rate of heat transfer. And then these are all the rates of change of the energy in the system. So we need to be able to solve conservation or first law equations on a rate basis. Here's a problem. An electric motor draws a current of 12 amps with a voltage 120 volts. The output shaft delivers a torque of 10.2 Newton meter and a rotational speed of 900 revolutions per minute, RPM. For steady state operation, determine for the motor the electric power to the motor, the shaft power from the motor, heat transfer from the motor, and then calculate a motor surface temperature if the ambient air is 25 and H times A is 12 watts per meter, 12 watts per Kelvin. So make a little sketch. Here's our electric motor. Maybe it's sitting on a stand. And the inputs on one side are the positive and negative wires that brings in and returns out a current of 12 amps. And the voltage across those wires is 120 volts. So the electric power to the motor would be simply W dot electric to the motor is equal to the voltage, let's call it E, the EMF, electromotive force, times the current, and we have 120 volts times 12 amps. Is that 1440 watts? A volt times the amp is a watt. And they said, we want the answer in kilowatts. So the electric power is 1.44 kilowatts. Box it. Make sure there's a dot on top of that W. That indicates a power. And that's the answer to part A. Yes, sir?
The formula sheet says that it's negative. Is that?
Sometimes what we do is this word trumps the traditional sign convention. Okay. So it says into or to the motor. And so there you go. Okay. When in doubt, say that this is to the motor. Provided energy to the motor. Yeah. Then with the other side of the motor, we have a shaft, and that shaft comes out. Maybe that shaft is running a pump or a fan or turning something or lifting something. And so So what do we have is we have the shaft is rotating at a particular rate. We use omega, the Greek letter omega for the rate of rotation. And it has a torque in that shaft, meaning that something doesn't really want to be turned, so it has a back torque on it. And so the motor is supplying a torque in the shaft at that rotational speed. And so the torque, what symbol do we use there? Tau. Tau, Greek symbol tau for torque. So let's work out what omega is. Omega is how many radians per second, but we're given the rotational speed in 900 revolutions per minute. Well, we do a unit conversion that one revolution is how many radians? 2 pi radians. A full circle revolution is 2 pi radians. And then a minute is 60 seconds. And so omega, we should convert that over, and we find that it's 94.2478 radians per second. Now I write that out to emphasize, don't truncate in your intermediate steps. And it's so frustrating. I'll be grading a final exam in Thermo 2, and somebody will just willy-nilly truncate to 1 or 2 significant digits and then proceed and then give me the final answer to 4. Don't do it. It doesn't make sense, okay? So keep all your intermediate digits. I've probably said that enough already this semester, haven't I? All right, how about then the torque? Well, the torque was given to us in 10.2 Newton meters. So that's a Newton times, look at this up here. That's a Newton times a meter. One time I was teaching class, Thermo 1, and I know you give them the current, you give them this and that, you give them the torque, you ask them to compute the power, like we're doing right now. Sometimes you give them the shaft power, you give them the rotational speed, and you ask them to compute the torque in the shaft. And I did. That semester I asked them to compute the torque in the shaft. And I got a bunch of answers back in units of joule. Professor, a Newton times a meter is a joule. And I was surprised. And I didn't know what to do. So I had to sort of like say, prevent that student from coming out with an engineering degree from UTSA, going into the workplace and say, I learned that torque can be represented in units of joules. And so how do you prevent somebody from doing something you don't want them to do? You make it painful. So they lost points, and they were pretty upset. And they argue with me, but isn't a Newton times a meter a joule? That's a great unit for energy, and yes, that's a joule, but a torque is never, ever in engineering reported in joules. Can you never do that again, please? It's going to save you embarrassment in the workplace. Anyway, I didn't know what to do because it's like, you're right, Newton times a meter is a joule, but that's not how we report torques. Okay, so let's do then the W dot for the shaft, and that's coming from the motor. So the sign I'm going to say is positive coming out of the motor, and it's just going to be calculated as the omega times tau, the rotational speed, times the moment of the force of the torque. And we calculate that this is 0.943 kilowatts. So W dot shaft, and then we box it. And then if we like to, we say this is the answer to part B. All right. What is the heat transfer from the motor? Well, I would do this. I would put a little control volume where I'm focused on that mass or that system, which is the motor. And I have some power coming in. The power coming in, we already calculated in form electric, is W dot electric. We have some shaft going out, W dot shaft. And we have some rate of heat transfer in kilowatts from the motor, something like this. coming out. Little squiggly line often is used for heat transfer, and that's Q dot. And so from a conservation of energy, we would say the rate of change of energy in that system that surrounds the motor, which is the motor, with respect to time, is equal to the rate it's coming in electric power coming in, minus the rate at which it goes out, shaft, minus the rate it goes out with heat transfer off the surface. One in, two outs. The electric energy that flowed in, either through friction, turned to heat and was transferred out, which we don't like a lot of in our motors. We don't like, motors are not, the purpose of motors is not to make the air around the motor warm. It's to turn a shaft. So we want most of that to go into turning the shaft. So anyway, it's operating at steady state, so that's zero. There's no accumulation of energy in the system. And so the balance gives us that Q dot is equal to the 1.44 kilowatts minus the 0.943 kilowatts. And this is where you would make sure to have all your units, but those were all the units on the 1.44 kilowatts. Anyway, you come out with 0.498 kilowatts. And that's from the motor to the room. And that's the answer to part C. The motor surface temperature if the ambient air temperature is 25 degrees C. Well, we go back to our Newton's law of cooling. This is one of those few examples where we go to an equation to describe the rate of heat transfer. The surface of the motor minus the temperature of the air that surrounds the motor. And so we find that the temperature of the surface is the air temperature plus the rate of heat transfer divided by the product HA. A is the area of the motor, and H is the convection coefficient. Well, they don't give us them individually. They give us HA as a combined value. It's equal to 12 watts per Kelvin. So we stick our numbers in. It's 25 degrees C plus 498 watts per 12 watts per Kelvin. Notice that I wanted to avoid that kilo on the watt, so the units are a little clearer. And this is 25 degrees C plus 41, whoops, I can write 41, 41.5 Kelvin. True? Okay. I'm going to pause right now, and I want you to give me the final answer for TS. I'm going to walk around the room and see how you do. I want you to handle this unit conversion challenge. All right, so here we go. Let's do this again. Why did I pause? Because I know you can have the simplest little task ahead of you, like adding temperatures, and you can introduce a very common error. So one strategy somebody says is I'm going to take and I'm going to convert 25 degrees C into Kelvin. So I add 273.15 to it, and I'll get 298.15. I'll add the 41.5. I'll have it all in Kelvin, and then I'll take off the 273.15 again, right, to get it back to degrees C. Let me just explore that a little bit because I need to scroll down, sorry. See, I took the 25, I add 273.15 to get it to Kelvin, I added the 41.5 to get it to Kelvin, then I wanted it back to degrees C, subtract 273.15. Didn't the plus and minus on the 273.15 go away? Could I have just said, hey, that's equal to 25 degrees C plus 41.5 degrees C, which is a temperature of, help me a little bit, 66.5 degrees C. True or false? Oh, that gives us a little heartburn because hey, you just willy-nilly converted Kelvin to degrees C. 41.5 went to 41.5. Your bottom line is you're right. How can you do that?
You had told us not much you're looking for the 1 degree Celsius temperature change is equal to 1 K.
So a temperature change of 1 degree C is precisely a temperature change of 1 Kelvin. You're absolutely right. You're absolutely right. And this was a temperature change of 41.5. That's not an absolute temperature. That's really cold if it's an absolute temperature. And so there you go. Okay. Hopefully you can do that quickly on an exam. And so this is our surface temperature of our motor. And that was the answer to part D, and we're done with this problem. Any other comments or questions?
Were you asking for Celsius in the question?
Yeah, let's take a look at the problem statement. Actually, I left it ambiguous.
Isn't normally unless you specify, you just go with whatever's in there.
If I don't specify, I'm not going to, give it to me in something that's reasonable. Yeah, either Kelvin would have been fine or degree C.
So why didn't it work to convert it to Celsius? Convert Kelvin to Celsius and then add Kelvin?
I'm not certain what you were doing there. First of all, this is a temperature. Like I go out and I say, hey, it's 25 degrees C. Yep, that's reasonable. This was never the temperature like go outside. Hey, what's the temperature outside today? Oh, the air temperature is 41.5 Kelvin. That's like really cold. So I don't know exactly what you did in your math, but take the C, put it to Kelvin, add it, then take it back. You'll get the right answer. Do you remember what you did?
Well, we converted Kelvin, so to get from Kelvin to Celsius, you subtract 2.
So it's super cold in degrees C.
And that's why everyone was getting negative answers.
There you go. That's why. Yeah. So a super low temperature is unreasonable. Not the interpretation of 41.5 is the temperature change.
I did have a question.
Yes, sir.
On our formula, it says that it's Q dot minus W dot, so why did...
Well, we just like in statics, you have a free body diagram, and that trumps the assumed direction. Without a free body diagram, if I say F of X, it's in the positive X direction. If I say F of Y, the force it's in the positive Y direction. But if I got a free body diagram, that defines the direction. So you have to have some illustration and or some wording that basically says this is to the motor, and draw it to the motor, and from the motor, show it from the motor, and from the motor. So I know it's a little unsettling. It's nice to always use equation sheets and have no ambiguity, but we take ownership, but just like of the free body diagram, we take ownership in thermodynamics of the energy balance equation. Now we talk about basically a generic power cycle. So here's a system, and we just draw that as a big box. It's pretty arbitrary what's happening inside this system. But this system, if it's a power cycle, is something like a heat engine. And the heat engine takes in some heat transfer, a lot of it from a high temperature source where it's hot. You're burning something to make a hot environment, and then you transfer the heat out of that flaming ball of fire, that furnace. Okay. And you want to convert as much of that energy into work net out of the cycle. So instead of showing some work here in, some work here out, just talk about the net work out of the cycle. And there's no way to do that without throwing some heat out to the low temperature environment. Often you have to have lake water or air or something to dissipate or throw some heat out into the environment. Okay? Now, one of these things is no matter how much you remove of QH, TH does not change. It's constant. And just like I go outside and I say, hey, I'm going to warm it up outside. It's 99 degrees. Here I'm going. I'm going to exhale real heavy, a lot of heat. Did I heat it up outside? No. I didn't heat it up. So basically that low temperature is constant as well. They don't change even if you dump some heat into it. Now you can show this generic power cycle either on a mount basis where it's Q in kilojoules, or you could put it on a rate basis. Either way, it works. So either this or Q dot H and W dot cycle and Q dot L. All it is the difference between kilojoules versus kilowatts, right? Kilojoule per second is a kilowatt. So you can't mix them. They either are amount of heat and amount of work, or it's a rate of heat or a rate of work transfer. Okay. Now, what this is, the two things we want to cover here. One is a first law, or energy balance. Energy is conserved. So you just say the ins is equal to the outs, kind of like your bank account. It's running at steady state, so there's no accumulation or depletion. What comes in goes out. So what is my one in, QH, or Q dot H, if you want to put that? What are the outs? Work of the cycle and QL. Here again, we kind of overridden our sign convention. Our illustration shows us the direction of QH and the direction of QL. And both are positive. One's in, one's out. Okay? The second thing is that you have the definition of what we like to accomplish, the thermal efficiency. What do you mean by thermal efficiency? Well, it's given the Greek letter eta. E-T-A, eta. Greek. That's what this textbook uses for the thermal efficiency of the cycle. And that's a ratio of what you want the cycle to produce, to give you. What do you want a heat engine or a power cycle to give you a lot of? Work. You want a lot of W cycle out, large W, divided by what you have to pay for, what you have to provide. What's expensive?
Coal.
The coal to burn to create a large QH. So that's what drives the system. That's the expensive part. Now, somebody says, what about QL? Through taxes, maybe. Thermal pollution tax, maybe. They don't currently have a thermal pollution tax, but in the future, maybe there will be, kind of like a carbon emission tax, which is coming, probably. I thought it would already be here by now, but it's not. Okay. So, this is the thermal efficiency. That's the definition. Sometimes you put 3 bars right there. Now we can solve a lot of problems. Whenever you're given a problem here, think about making sure the first law is satisfied. Energy is conserved. And then often compute the efficiency, or maybe they give you the efficiency. So for a general cycle where there's a Q in, a Q out, and a work of the cycle. So just like what we have, here is a Q in. Here is a Q out, positive out. Here is the work of the cycle, W cycle. The heat transfer in is 60 kilojoules. The heat transfer out is 30 kilojoules. Calculate the net work out of the cycle. The net work out of the cycle. I'll just pause and let you write that solution down. So let's go through it. So what we have is like $60 in, $30 out, meaning this is $30 out. You know, that's just units of kilojoules. So by observation or quick deduction that 60 in, you have 30 out with the heat, hence the work of the cycle is equal to 30 kilojoules. And that's out in that positive direction, the sign showing you on the illustration, answer to part A. Then the thermal efficiency, Greek letters eta, is equal to the ratio of the work of the cycle that you wanted divided by the Q in. which is 30 kilojoules divided by 60 kilojoules. So eta is 50%, or eta is 1/2, or eta is 0.5. Those are all acceptable. Okay. The generic refrigeration cycle, so this purpose of this cycle is to basically move heat out of something that's low temperature. So bring in the heat out of something that's low temperature. Why? Because it's leaking in from some other part of the system. The inside of your refrigerator would like to stay cold if it was perfectly insulated. But you have a refrigeration system, part of the refrigerator, to keep it pumped out. And you have to dump that heat to some high temperature, the inside of the kitchen or the outside of the house in the hot day in August. What do you have to do? You have to supply. You're not going to be able to have a refrigeration cycle, have it run and sell electricity back to CPS. Just the opposite. You got to purchase electricity from CPS. True? And so now you have an energy balance. This energy balance says I have two ins, QL plus work of the cycle is an in, and I have one out, QH. Or if you wanted to put it in rates, put Q dot L plus W dot cycle equal to Q dot H. Either one works, but it's the energy balance. Then you have the efficiency. Well, here, I forget what the book uses. I think gamma. I don't like gamma. Why not COP, coefficient of performance, for a refrigeration cycle, defined as the ratio what you want divided by what you had to pay for. You have to think, refrigeration cycle, what did I want? Do I want a large electric bill from CPS? Do I want a large QH? Do I want to heat up the inside of my kitchen? Or do I want a large QL, keep the refrigerator cold? So it's QL divided by what you had to pay for, W cycle. Let's go to the next one. It's a generic heat pump. This term may be less familiar to you right now, but I think some of you may know that inside your house in the winter, you have a heat pump system. Some of you do, probably about 5-10% of you do. And that heat pump system's running to provide a nice warm environment to the warm inside of your house when the outside is very cold. The outside is very cold. Yes, sir?
Is that supposed to be TL at the very top, or is that TH as well?
This is TH right there. Thank you very much. Yep, TH. And this heat pump requires the work of the cycle to run. So we still have our same energy balances. They're all the same. QL plus W cycle is equal to QH. Then the coefficient of performance, but it's not for refrigeration, it's heat pump. What do we desire in a heat pump? A large QH. What do we have to provide? W of the cycle. Now, you say, why don't we just have electric resistive heating? Well, if you do, then it's just 100% this way. But what you can do is you can provide maybe 1 kilojoule of energy, and you can grab from the outside, which is cold, the cold winter day, you could probably grab another 1 kilojoule of energy and provide 2 kilojoules of energy to the home to keep it warm by only paying for 1 kilojoule of energy from CPS in the form of electric energy. If you had electric resistive heat, it's 1-to-1. With a heat pump, you can get a better amount, more heat for the same purchase of electricity. That's why they sell heat pump systems. Okay. A little quickie is that the coefficient of performance of the heat pump system is QH divided by W cycle, true? But I can rewrite this QH as QL plus W cycle divided by W cycle. All I did was use the first law right there. And so that's equal to 1 plus QL divided by W cycle. True? What was the definition QL divided by work of the cycle? We find the coefficient of performance for the heat pump system is 1 plus the coefficient of performance for the refrigeration system. Often these are the same type of system. It's just what you want out of it. What is it there for? Is it to provide cooling to low temperature, pull heat out of low temperature, or provide heat to a high temperature? And the coefficient of performance of the heat pump is 1 greater than the coefficient of performance for refrigeration cycle. These are just little problems. Consider a general cycle with heat transfer in of 60 kilojoules, net work in of 30 kilojoules. So when it's coming in, that's either a heat pump or refrigeration. Okay, so if it's heat coming in of 60, that must be coming from the Q low. The work of the cycle coming in is 60 kilojoules. What is the heat going out? Can you tell? Oops, I wrote it wrong. This is 30, isn't it? What is the heat out? 90 kilojoules. So the heat transfer out of the system, part A, is 90 kilojoules. What's the coefficient of performance, assuming this is a refrigeration cycle, COP refrigeration? It's going to be what I desire, 60 on the QL, divided by what I had to provide, 30. So the COP for the refrigeration is 2. Notice that the efficiency of a heat engine for a power cycle is between 0 and 100%. But coefficient of performance, you can have 2. You wouldn't typically put 200%, but you could write it as that. Okay? Or it could be, it typically is greater than 1. Okay. Doesn't have to be. It can be lower than 1, but it can be greater than 1. And then the coefficient of performance for the heat pump. Well, what do I desire? I want 90 divided by 30. Hey, COP of the heat pump is 3. Just consistent with what you talked about. The heat pump, you add 1 to the coefficient of performance for the refrigeration for the same operating conditions. Boy, I wanted to solve this problem. I'll delve into it and then we'll probably have to leave. A gas in a piston cylinder assembly operates a cycle where the states are listed in the table. 1, 2, 3, volume 131, pressure 500, 300, 100. Sketch the PV diagram for the cycle. So go ahead and sketch pressure, volume. Maybe because you see the volume is in meter cube, you label it like that, and you go 1, 2, 3, try and draw it a little bit to scale. I know I don't often do that. Then 100, 200, 300, 400, 500, 500. This is all kilopascal. Then there's 400, and there's 300, and there's 200, there's 100, and there's 0. All right, so where is state 1 on this illustration? State 1 is at that point, isn't it? Isn't that where state 1 is? How about state 2? Right there, state 2. And so the process from 1 to 2, they didn't give me any information, but I'm going to assume, with lacking information, that it's a straight line. Okay. Straight line, is that compression or expansion? Expansion, is it positive work, negative work for our sign convention? If the gas is doing the expansion, it's positive work with respect to the gas. How about state 3? We're back to here. Assuming straight line. It add 3 to 1 to close the cycle, because it is a cycle. There you go. Now, it's sketched on a PV diagram. Is this a power cycle? I'm going to pause, walk around. Is it yes or no? Is this a power cycle? If it's not a power, it's either going to be a refrigeration or heat pump. It's either one of those 3 at this point in our discussion. But power, yes or no? Is it a power cycle?
That made me think it would be a power cycle.
Yeah, this is all in a piston cylinder assembly. And so we are describing that condition. And so what it is this is expanding at relatively high pressures. What's the average pressure it expands at from 1 to 2? I know it starts at 500 and it ends at 300, but what's the average pressure? 400. And then what's the compression average pressure? It goes from 300 to 100, 200. So it's expanding at high pressure, great for workout, and compressing at low pressure, good to have low work in. And so the work out is the area under the curve during the expansion. That's this area under this curve, all this area. And then we have the work of the compression is the area under the curve. And so what is this area that is the difference, so to speak, or that's the enclosed area of the cycle. And the closed area is a visual representation of the work of the cycle. And because it's this direction, I can't remember, clockwise or counterclockwise? Clockwise on a PV diagram, meaning it's expanding at high pressures and compressing at low pressures. It's a great power cycle, or a power cycle. I shouldn't say great. So yes, this is a power cycle. You ready to solve a problem, this problem, continue this problem?
So if the work for the cycle is positive, does that mean it will be a power cycle?
That's correct. That's correct. So now they give us the same information but more here. They say that for process 1 to 2, the change in internal energy is 650 kilojoules. So U2 is greater than U1 by 650 kilojoules. And for the process 3 to 1, Q is 1,000 kilojoules. Determine the work for each process. So resketch the PV diagram. Okay? This was 1 to 2 to 3 and then back again. And I need to calculate the work 1 to 2, the work 2 to 3, the work 3 to 1. And then I need to get the Q1 to 2, the Q2 to 3, and the Q3 to 1. I need 6 answers for part A, 3 of them, and part B, 3 of them. Okay. Well, of the works, which one is the easiest to compute? 3 to 1 because it's 0. Now, how about the work 1 to 2? Integral PDV. But you know what? We already know the average pressure and the volume change. It goes from 1 to 3 meter cubed. And at an average pressure of 400 kilopascal. I can do that graphically. Or I can go get a straight line through 2 points and do it analytically. But hey, engineers like to do things graphically. And so what is the work 1 to 2? 400 times 2. 800 kilojoules. Positive. How about work 2 to 3? Yes? It's the integral PDV, which is the average pressure times the volume change, V2 minus V1. This was 3 minus 1 meter cubed. The average pressure was 400 kilopascal. So 400 times 3 minus 2, which is 2, 800 kilojoules. Do the same thing now for 2 to 3. Remember, this starts at 500, goes to 300, then from 300 goes to 100, so the average is 200 right there for this average pressure during compression. So what is the work 2 to 3? Negative 400 kilojoules. See how easy it is? Professor, give me this on the test. Well, I can't. Not exactly. Okay? Now, the work is done. How about the heat transfers? Well, we usually can't calculate this by like an integral property, D property, or something like that. We did that great for the work. But for the heat, we kind of have to use the first law, which says Q1 to 2 is equal to U2 minus U1 plus W 1 to 2. I just rewrote it by throwing W on the other side, right? So I got rid of that negative sign, threw it on the other side. And then I looked at, hey, I just calculated the work 1 to 2. If I was somehow given this information, I can get Q 1 to 2. And there it is. So we have 800 plus 650. That's the hard part. Is that 1450 kilojoules? Yes, no, or maybe? All right, so it's 1450 kilojoules. How about from 2 to 3? I wish they gave me the change in the U's, but they didn't. It's called SKIP. We'll come back to it later. How about Q 3 to 1? It's given to me 1,000 kilojoules. Now I'm really stuck because I can spin my wheels trying to write the first law for the process 2 to 3. Q 2 to 3 is equal to U3 minus U1, 2, plus the work 2 to 3. Okay? I mean, it's not, maybe I should say I can do it that way. It's just I'm going to have to figure out what is the change in the U's. Okay? But one thing that I can do is I can go and use this information. What is the work of the cycle? The sum of the works over all the processes of the cycle. How is it related to the Q of the cycle? That's how it's related, the way I wrote it. So the magnitude of the work net out of the cycle is equal to the net heat in. How did you get that? Okay, well, do this. Write the first law for the whole cycle. So let's do work, let's do it this way. I'll write it like this. Q 1 to 2 plus, minus work 1 to 2 is equal to U2, U1. Make sense? Let's write it another time for the second process. Q 2 to 3 minus the work 2 to 3 equal to U3 minus U2. Let's do it again. Q 3 to 1 minus the work 3 to 1 is equal to U1 minus U3. True? I have three equations. Sum them up. So what do we get on the bottom down here? We get Q1 to 2 plus Q2 to 3 plus Q3 to 1. We also get minus work 1 to 2 plus work 2 to 3 plus work 3 to 1. And then over here, it's like, hold it. That U1 and that U1 cancel. That U2 and that U2 can't. That U3, that U3. Guess what? It's equal to 0. So I look and I say, this is nothing but Q of the cycle minus nothing but work of the cycle. That's equal to 0. That's what I just wrote. True? So I look at it and I say from this equation, let me try and back up a little bit. As I look at this equation, I say, I'm looking to calculate this guy as my unknown. Q 2 to 3. I know Q to 1 to 2, that's 1450. 3 to 1, I know that's 1,000. Work 1 to 2, 800. Work 2 to 3, negative 400. Work 3 to 1, 0. That's how I calculated for Q 2 to 3. It may be a little more work than you like. Let me see if I have a value for that. Well, fine. Figure it out. Just do it by myself. What's the, do this, work of the cycle? 400 kilojoules. Okay? What is then Q of the cycle? 400 kilojoules. So we have 1450 plus Q 2 to 3 plus 1,000 equal to 400. So Q 2 to 3 is 400 minus 2,450. And so Q2 to 3 is negative 2,050 kilojoules. You're really throwing some heat out of the cycle on that process 2 to 3. The last one, what's the cycle thermal efficiency? Well, you say to yourself, what did I really want to accomplish? A large work net. That's 400 kilojoules. What did I have to supply? Well, I had to supply 1450 kilojoules in the process 1 to 2, plus I had to supply 1000. The net, the N is 2 parts. It's Q. See, there's 2 positive N's. This is an N, and that's an N. So the total heat transfer in is 2,450. So the thermal efficiency is, and I don't have any notes in front of me. Somebody want to run that on a calculator, please? So what do we get? 14 point? Did you say 14? Okay, 16.3%. You say, boy, that's lousy. You know what? There's a lot of stuff out there that's not that good. And you know, when they started steam engines, kind of like really using them in industry, 0.0 or 0.5% thermal efficiency. And then if they could get it to 1 or 2%, it was a huge improvement. And now you're looking at automobile engines, maybe 30% thermal efficiency. Really, really good fire, gas and coal-fired plants owned by CPS, City of San Antonio, operating cities, maybe, I don't know, 40%. Really high-end gas combined cycles, 50+%, but not a whole lot over 50. And I've seen bragging points like up like close to 60, but that's really highly engineered, and I don't know if they're able to sustain that high efficiency over long time periods, or if it's just like you got it running great, perfect, right? But a little something comes in and perturbs the system and your efficiency dives. So, but yes, they are out there, engineers, a lot of them working in this field of energy and energy transformation, and efficiencies are huge. It makes big bucks. Well, we're done with this material. Thank you for allowing me to talk to real people for this recorded lecture, and we'll see you test day.